Welcome back, Physics 2. I hope you all had a good weekend for those of you that are just staying on track. So in today's lecture, this is Monday's lecture, part 1, week 13. So we're moving along in this semester, and we're going to keep moving along in chapter 20. So, and that is, of course, in matter and interaction. So we're going to look at potential energy for a magnetic dipole. So what you're going to keep seeing in these next couple of chapters is that this is the part where we really start to bring all of these concepts together. So we've already connected our electric and magnetic forces, and we use that to find torque, which was a concept from Physics 1. Now we're going to start looking at potential energy for magnetic dipoles. This is, all of the introductory physics sequence is really cool, but I think this is especially fun. Okay, so magnetic dipoles, if allowed to move, will turn upward, will turn towards, it may not be upwards, towards being aligned with an applied magnetic field. They like to they like to be like the cool kids. They want to line up just right. So basically not me in high school. All right, so this implies that the dipole is associated with lower potential energy. Now, we are talking about energy. We are talking about potential energies. So clearly what's coming up now is going to be some work. So we need to work. And by that, I mean we need to do some work calculations. So if we think back to our larger picture, so if something is allowed to freely move, and we're going to be dealing with rotational movement, so we need to, rotational movement, and when you have rotational movement, you have a constantly changing theta. So theta is changing. So what we're going to think about is what's going to happen. So we've got our bar magnet, which is essentially just a magnetic dipole, and it's allowed to move so that it can align with whatever field it wants. And so it's going to move through some angle theta. So we want to see what happens as it would go from theta initial to theta final. So it's going to rotate, and specifically, what work would be required for this. So we're not thinking about momentum principle, we are thinking about energy principle. All right, so work is equal to the change in magnetic potential energy. That's magnetic potential energy. So we can set up our work integral, and we're going to go from our initial theta to our final theta to IWB sine theta h over 2 d theta. And so this is equal to IWHB. So we're going to pull our constants out in front, integrated from the initial theta to the final theta, sine theta d theta. All right, so now we're going to go ahead and solve this integral. So here's our integral. And so the change in magnetic potential energy is equal to IWHB minus cosine theta from theta initial to theta final is equal to IWHB cosine theta final minus cosine theta initial. And so the change of magnetic potential energy is equal to delta minus mu b cosine theta. And this follows up from our discussion in part 2 of Thursday's lecture. So it might be worth going back to that lecture and giving that a quick review at the end just to get caught up. So where mu, our magnetic dipole moment, is equal to current times area, which is equal to current times width times height for the original square section. So here we had our square wire. It's current I. Okay, so the magnetic potential energy is equal to minus mu b cosine theta can also be written as the magnetic dipole moment dotted with the magnetic field. So we see that this is just the cosine notation for the dot product. All right, so moving along. Now let's say we've got some magnetic fields, and they're all pointing up. And we've got some different magnetic dipole moments. So for this one, mu is going in the same direction. Here we have mu going perpendicular, mu going in the opposite direction, and mu going perpendicular again, but in the opposite direction as the first one. All right, so for these, which one of these is going to have the lowest potential energy? All right, so to think this one through, we said that magnetic dipoles like to align themselves with the applied magnetic field. And so this one is aligned with its magnetic field. So this is going to have the lowest magnetic potential. And so mu and b are in the same direction. So it's a cosine of 0 is equal to minus mu b. All right, so this also implies that it is the most stable. It's not going to want to twist. It's very happy where it's at. Okay, so using that logic, then we could imply then that over here we have the highest potential. So right here. So here we have highest potential energy. So mu and b are in the opposite directions. So minus mu b cosine 180 degrees is equal to plus mu. This also implies this is the most unstable. So even a little bit of displacement and it's going to want to twist. It's not happy. It wants to go to the point of lowest potential. Now these two, they're just medium. They've got more potential than our stable position, but not as much potential as the most unstable. So they're both just somewhere in between. These two are the interesting ones. All right, so moving on. So we've already talked about how the twist on magnetic dipoles, but now we're going to flesh this out a little bit deeper into the net force on a magnetic dipole in a magnetic field. So we want to look at force on a magnetic dipole in a magnetic field. All right, so if you recall, we've already talked about all magnets are dipoles. There are no magnetic monopoles. There are no magnetic monopoles. You cannot have a north hanging out by itself. It always has a south to go along with it. Okay, so we could look at, here we have a bar magnet, which is a magnetic dipole, and we've got a current carrying loop right here, which is also a magnetic dipole. So we would have our magnetic dipole moment is equal to I pi r squared for the loop. And so what we want to think about is we've got this magnetic dipole in a non-uniform magnetic field. So we know that the magnetic field changes as a function of distance from the loop, so it is not uniform. And so it's going to experience a non-uniform force. So we want to think about the force on that current carrying loop. So I'm going to draw a couple of things on this loop, and we're going to build towards each of them. All right, so current I is in this direction, and then we have magnetic field. We've got field here, and then we're going to have, as we will see, let's put that in a different color, df cosine 90 minus theta. So theta is here, and theta is here, and then we have df cosine theta 90 degrees minus theta. Okay, we'll flesh this picture out in more detail, but for now, this is what I want you to have in mind. Okay, so let's think about the force on the current carrying loop from our dipole magnet. So force on the loop from the magnet. So each segment of the loop experiences a force. So each segment, so we're going to take our approach of cutting up into pieces. And it's going to experience a part of a force that is equal to the current times our segment piece delta L crossed with a magnetic field. So for the horizontal component, we have df cosine of 90 degrees minus theta, which is equal to df sine of theta. And the vertical components cancel. So we looked at that when we previously derived the magnetic field for a loop. Okay, so the net force, now that we've got our segments, we want to go ahead and sum them up. So we're going to integrate. So IB sine theta, and we're going to integrate this with respect to dl. So this is equal to IB, and to go all the way around, we're just looking at the circumference, so dl is going to be 2 pi r sine theta. So this is the result of that dl integration. Okay, so moving right along, if you recall, mu is equal to IA is equal to I pi r squared. So our F net, which is equal to IB 2 pi r sine theta, becomes mu 2b sine theta divided by r. All right, so this is one way to think about the net force when you're dealing with a situation with a magnetic dipole, like a bar magnet, and a current carrying loop, but it requires a lot of information. So we had to know a lot about this setup in order to get to this result, or if you wanted to actually calculate this, you'd need to know a lot. But you can also determine net force using the potential energy and the magnetic dipole. So I'll write that down. Net force and magnetic dipole. All right, so let's take a look at that. So if we move a dipole from a region of a low magnetic field to a high magnetic field, it would make sense then that the magnetic potential energy will change. So our magnetic potential energy is equal to minus mu dot B. If B changes, then mu B changes, unless mu also changes. So dipoles want to go to areas of lower potential. So if you release your object, let me spell release correctly. If you release the magnetic dipole, it would move towards lower U while picking up kinetic energy. So this is just a physics 1 concept. If K increases, then U must decrease. If U increases, then K must increase. Why? Because energy is always conserved. What you got is what you got. All the energy in the universe that has ever existed and ever will exist was there from the moment time began. All right, so, but this is useful. We can use this. If we want to prevent kinetic energy from changing, so we want to prevent delta K non-zero, then we can keep delta U the same. Then we need to apply a force to move the object at constant speed. So as we all know, K is equal to 1/2 mv squared. So if V1 is equal to V2 and there is no identity change, then K1 is equal to K2 and delta K is equal to 0. All right, so once again, if we're applying a force over a distance, so we need a force applied over distance, so we need to work. All right, so what you're looking at there is you've got, here's our bar magnet, south, north. If it's one of the bar magnets in this lab, it's been dropped many times, so it'll be nice and weak. And so we've got a bar magnet here, we've got another magnetic dipole. We don't know what it is, we just know it's a magnetic dipole. So we're gonna have the magnetic force in this direction, and then to counter that, we are gonna be applying a force. So F by U. And we have our magnetic dipole moment, mu, which is pointing in the opposite direction. And we've got the field from B1 and B2. We're going to move it some delta x. All right, so we have, write a few more details. So magnetic dipole aligned with a magnetic field from another dipole. So the bar magnet has a non-uniform field that is proportional to 1 over x cubed. So assuming far enough away. So, and that's a pretty safe assumption. This little dipole is far enough away from this non-uniform magnetic field from this bar magnet. Okay, so by moving the dipole away, we are moving from a large magnetic field that is closer to a smaller magnetic field. And so the implication of that, leave this here off to the side so I can bring the picture back to play. So we've moved from big B to little b. So the magnetic potential increases from minus mu b to less negative. Okay, so we know the potential is negative. We are decreasing the potential, so we're just making it from negative to less negative. All right, so the force from U times delta x is equal to the change in magnetic potential. So if there's no change in kinetic energy, then the work is only changing the potential. So then we have minus mu B2 minus mu B1. And this is equal to minus mu B2 minus B1, which is equal to minus mu delta B. So once again, looking back at our picture, over delta x, we had a bigger field here, and then when we moved it to a smaller field, B2. Of course, both of these fields are coming from the bar magnet. All right, so as B2 is less than B1, this is greater than 0. So the force by U is equal to the change in magnetic potential divided by delta X, which is equal to minus mu, that's a delta B, over delta X, which gets us to minus mu dB dx. So we're going to look at the change in magnetic field with respect to the change in X. And this results in F sub X being equal to minus du dx. Oh my goodness, we've seen this before, haven't we? Wow. And F sub X is equal to minus d minus mu dot B over dx, which is equal to mu dB d, that's an x. It's a very, very poorly written x. All right, so obviously in order for this to be non-zero, the B field needs to be non-uniform. So if B is uniform, then the change in B is going to be 0, so dB dx is equal to 0. All right, so this is a very useful result, and we can take advantage of it, and we should. I mean, that is why we derive things in physics. It's to take advantage of what we find. All right, so we can use this result to calculate the force of one bar magnet on another. So we have two bar magnets, south, north, and south, north. So we have mu1, mu2. These are vectors. And so the magnetic field from one magnet, so is, oh my goodness, B1 is approximately mu naught over 4 pi 2 mu1 over x cubed. So we've seen this result before. I believe it was chapter 17. And the force is approximately 3 mu squared mu naught over 4 pi 2 mu1 over x to the fourth. So those of you in 211, you need to, on your own, show this is the negative gradient of magnetic potential energy. All right, so moving right along into a discussion of motors and generators. So I'm going to go ahead and get a fresh sheet for this. So all of this discussion leads up to how we can understand electric motors, which is an application of magnetic torque. So electric motors of magnetic torque. And of course, for those of you taking the class with me, this is of course leading up to your electromotor assignment that is your final lab. So we know that when we have current carrying cables, we know that coils want to go to their most stable position. And for a motor, you basically want something that's going to continue to turn. So basically you want to say, oh, you want to go to your most stable position? Here it is. Oh, it's moved, it's moved, it's moved. Got to keep turning, got to keep going, got to keep going, got to keep producing that power. So basically we devise a mechanism to keep the coil turning. So one way to do that is you can make the direction of current to switch at the moment it reaches stability. So one method is something called a split ring commutator, which will automatically change directions of a current at just the right moment. So you could do this with a split ring. So, and motors, so you've got a current carrying wire in a magnetic field that's constantly rotating because it wants to find stability. And these can be driven with either DC current or AC current. So the current that you have running through your households, this is AC current or alternating current, and the current that you've seen in lab setups where we've had batteries and light bulbs and wires, this has been DC current or direct current. Either one can be used to perform a motor. So for those of you who are building the motor, you can get bonus points if you, in addition to building a functioning direct current motor, if you also are able to build a functioning alternating current motor. And I will tell you from my own personal experience, it's a little bit trickier to do. And to get working. The theory is easy. Getting it working is the hard part. Like all experimental physics, the theory is always so beautiful and perfect. The practice is always so messy and everything breaks. And the laser never works. And the vacuum components never seal. I'm not bitter. All right, so building on this idea of motors and our discussion of motional EMF, we can get to electric generators. So we want to think back to motional EMF, which is where we used, we had a bar on rails. We made a little circuit going through a magnetic field. And we were able to use this to drive a current. So there's a couple issues from a practical standpoint of building a device like this, and that you'd need to have very, very long rails in order to get anything meaningful out of it. So this is generating a current, but in real life generators, we don't have these giant rails where we are putting bars on. What we actually do is we rotate wires through magnetic fields. So in real generators, we'll rotate wires through magnetic fields. And this will drive a current. And you can still make, through that charge separation. So that will still maintain the charge separation we talked about with motional EMF, but you don't have the problem of having enormous rails through that thought experiment we talked about before. Okay, so to talk about generators, we're going to return to our rotating loop. Oh, it's a better rectangle that time. Yeah. So here it is. It's rotating counterclockwise. We've got our magnetic field. Got our height. Okay, so Put a side view in there. Got our little theta angle changing. Okay, so let's say we rotate this loop with an angular velocity of d theta dt. So we're giving it a nice little omega. The tangential speed v is equal to omega h over 2. And our wire is h over 2 from axle. So our axle is right here in the middle. And so what we're looking at is magnetic force on a clockwise conventional current. So same setup as before. There it is. Okay. So the magnitude of the magnetic force at the angle theta on the charge carrier, Q, is going to be expressed so notice there's no vector because we're looking at a magnitude, QVB sine theta. And the motional EMF of one side of the wire, so EMF side is equal to QVB sine theta over Q is equal to B omega sine theta. Actually, that is a W, not an omega. All right, so, and the resulting EMF around the loop, so EMF around the loop is 2VBW sine theta. And if you recall, our tangential velocity is equal to omega h over 2, and sine theta is equal to sine omega t. And so EMF loop is equal to omega B HW sine omega t. And I believe last year I told myself, oh, I should change my omega or my W's to something else, and I forgot to do that. All right, so area is equal to H times W. So you could just sub that in for area there. So what if we connected a light bulb with a resistance to this circuit? Then, so we have add a resistor to the circuit. So then current is equal to omega B times area sine omega t over R. So we're just using delta V, I is equal to delta V over R. And this is how a generator works, only there's many turns of wire. So essentially we have the generator equation, only many turns. to multiply this by. So you would get a n factor of multiplication corresponding to the number of terms. Now, you might be thinking, wait. This is physics. We don't get something for nothing in this class. What about the power to turn the generator? And you're right. You don't get something for nothing. You do need power to turn your generator. So in order to turn the loop, we need an applied force. So force applied is equal to IWB sine theta at both ends. And this balances our perpendicular component, IWB sine theta. And when we move the loop, delta theta, so each end moves h over 2 delta theta. So work is equal to 2 times IWB sine theta times h over 2 delta theta. To get power, which is the change of work with respect to time, the change of work with respect to time is equal to 2 IWB sine theta times h over 2 d theta dt is equal to IB WH omega sine theta. And using I is equal to BWH omega sine theta over R, where theta is omega t, we can rewrite the change in work with respect to time is equal to I times Ri is equal to Ri squared, which is exactly what we saw the first time we looked at electric power, exactly as expected. Very cool. All right, so this wraps up chapter 20. Next up, we have chapter 21, electric fields in space. Of course, by that I mean all space. Very excited about chapter 21, and I will see you then.